hoping that most of you have gone through it. My screen is visible, I hope.
Yes, Sonam.
This is the same course, Association Analysis using Python, which we have covered in the last session. And there we talked about how can we find correlations between the variables, because understanding the relationship between the data is important to identify whether one variable can be responsible or can be predicted using the another independent variable. So we have two types of variables. One is the variable which we are going to predict, that we call as y, that is target variable. So target variable is also called as dependent variable, because we assume that our target variable price, for example, depends on several metrics like number of bedrooms in your house, floor area, carpet area, view side of your house. So number of attributes, it can depend on number of attributes. So we treat those attributes which are there as a part of your x as independent attributes, and y as the target variable. Now we need to understand whether the attributes which are there in x have any correlation with y or not. Whether if let's say my number of bedrooms increases, will my price of the house increase or decrease, or there is no effect? So understanding these relations is important, which we have done in the association analysis. Now we have seen how do we identify linear relationships, because in explore machine learning using Python, we talked a lot about regression algorithms, where we know regression algorithms works only on the linear data, where the two attributes or two variables should have a linear relationship between amongst themselves. So we have seen how to use scatter plot, how we can find covariance, correlation, and use different types of correlation matrix to understand to what degree those two variables are correlated to each other or not. Then we have also learned how to find association between categorical variables using hypothesis testing. Chi-square test we have used to do this, to check whether two variables are associated with each other or not. So your null hypothesis would be that they are not dependent, not related to each other. So considering that they are not related to each other, we try to prove whether our hypothesis is correct or not. So this is the part of hypothesis testing. See, if you want to understand more on this bit, what is hypothesis testing and what are these chi-square tests, what is these probability distributions, error probability distributions, maybe you can consider going for some mathematical topics which are there. I'll walk you through the topics. In today's course, regression analysis, in Prelude section, you will find a list of courses which you can take. If you want to go deep into this and want to really understand how these things work, if you're getting confused, you can prefer going for those mathematical courses as well. So a variation of chi-square test, if you just had to compare between two binary variables. Binary are also categorical variables, but if you have just two binary variables to be compared, which can take either yes, no, or disease or disease found, not found types of relationship, if you want to study, then we can go for phi coefficient test also. And phi is related to chi-square statistic in this way. So phi coefficient can come if you find chi-square also divided by the number of rows, so you will get the phi coefficient as well. So you can use any of the metrics to compare, to find whether the two, your target variable and your independent variable, they are dependent on each other or not, whether to go for the analysis or not, whether that analysis would be meaningful or not. See, it's not about let's say I ask you to find there are 10 students in a class, and I am asking you to find mean marks obtained by the students in a class. So ideally your equation should be the marks obtained by each of the students, find a sum of it and divide by 10. Okay, what if I divide it by 8? What if I divide it by 5? Still I'll get some answer, isn't it? But that might not be correct, might not be logical. It will not logically fit to what I'm expecting. I want mean. For mean, you have to find total number of observations, that is 10 in my case, and divide by 10 exactly. So it's not always about right or wrong, whether it should work or not. If you do not understand all these things, still you go ahead, create a model and start analyzing. Some output will come, but that might not be meaningful. It's all about the usability of your model which you finally come up with, and the usability and accuracy of the model will increase when you understand all these things, understand your data, and then work on it. appropriately. So now we are going to talk about today's market basket analysis. This is another feature very commonly used in data mining when it is frequently used by, you can say, e-commerce industry, like if they want to suggest you a few things. If you have purchased watch, maybe you would like to buy a strap also. If you have purchased milk, maybe you are interested in buying bread also. So when we go to supermarket, you might have seen they all stock things together. Like when you go to one section, you will find all things. If there's a bread section, so you'll find all the related things there. Bread, along with that, they'll give you butter also will be stacked over there. Jams also, sausages also, or jellies also will be stocked over there. Things related to, so items which are related to each other will be stocked all together in supermarket. Or let's say maybe there's a healthcare industry and they want to understand which all medicines are given together to a patient and what if impact do they have when they are given together. If that analysis has to be done, that means we are trying to compare the frequently occurring items. And this analysis is called market basket analysis. So here there's a data you can see. These are the customers who have purchased some items. So bill number is there, customer name who has purchased these items, contact number you can ignore for now. Items are there. So what if the supermarket wants to analyze which are the frequently bought items? You can make use of a priori algorithm. Have you studied a priori in your BTech or BE? There's a course called data mining and data warehousing. In that, this is the most famous algorithm which is taught in data mining. A priori algorithm is used. Basically, the fundamental algorithm to do this is a priori. Have you heard of it? A priori algorithm can be used to find. Okay, somebody says no. No? All right. Okay, it's okay. So let's see, how do we use a priori algorithm to find the frequently occurring set? See, if we do not go about the technicalities or the algorithms, then uh, how will you do it? If you have this data which is there on the screen and I ask you which items should be stocked together, if you have a supermarket and you have this data, based on this understanding you want to get an idea of whether I should put foot mats with the seat cover, or I should let's say somebody is buying seat cover, and now I want to suggest this person, maybe you are also interested in buying car cover. Yes, associated items. So how will you do this? Forget about algorithm, just looking at this data, what will you do? Any suggestion?
Maybe we will analyze the data and get some insights on based on the data, like how we can do the analysis, and that will help us to.
Correct. See, you have to analyze this data. This data has just 15 common things between the customers we'll identify. That's right. So all both of you are right. We'll find, see, I'll pick up one item, let's say seat cover. So I'm interested in knowing if a person has purchased seat cover, what is the next item I can recommend to this customer? So go back to your historical data, which is these 15 rows, and see what frequently the customers have purchased along with seat cover. So along with seat cover, car cover, foot mats, mud flaps. Okay, next time, seat cover, audio system, steering covers, foot mats. So two times I have observed that along with the seat cover, foot mats have come. Then in the sixth row also you can see along with seat cover, foot mats has come. Then seat cover is coming on 13th row along with seat cover. Alex purchased toolbox, but in no other transaction toolbox was purchased. So till now I got that along with seat cover, three people have purchased foot mat. That is uh, the observation till now. So 14, 15 done. So just by looking at this data, what I will suggest is maybe you are also interested in buying foot mats. If you have purchased seat cover, are you looking for foot mats also? Or then you can say people, 40% of the people who have purchased, 30% of the people who have purchased seat cover have purchased foot mats. Maybe you're also interested in it. So this is how recommendation systems work, and this is the basis for the a priori algorithm. It's just that the same process what we do in mind manually is converted to an algorithm. because there has to be a predefined step to it. We cannot just guess, do the guesswork and see. Here is the chart: seat cover was purchased, car cover was purchased, foot mats was purchased. So we find how frequently individual items was purchased. So this chart gives you an idea. Seat cover was purchased 4 times, audio system was purchased 4 times, and so on. So the total row and the last row of total tells us that foot mats was the most frequently purchased item, was the foot mat. So maybe in general, whatever was frequently purchased, you will suggest that. Along with toolbox also you recommend foot mat. Along with mud flaps also you recommend foot mats. That might be your approach of doing, but maybe we can go for the associated items like we did in the earlier step. Only 3 transactions were there where seat cover and foot mats came together. Now we need to have a support, a minimum support from the number of transactions to prove this. So a threshold should be there. Let's say seat cover and foot mat is coming 3 times. Seat cover, car cover was coming 4 times. Seat cover, mud flaps was coming 5 times. So which is it that you would recommend to the customer? And there has to be some threshold for comparison. So that we have to fix, that we call here in this algorithm as minimum support. Minimum support in terms of a percentage of transaction. So that can be pre-decided. So if 40% of the time, you see 40% of the times these transactions have come, or individual items have been purchased. So maybe 40% of the time, if seat cover and foot mats were purchased together, then only we will recommend it to the other customers. So that threshold, that benchmark has to be decided. That is called as minimum support. Minimum support in terms of percentage, or minimum support count. Count can be calculated minimum support times, that is 40% times the number of uniquely purchased items can give you the number of times, number of transactions in which you have to look at it. Wait, we'll take an example. I'll stop sharing. I hope the Excel is visible to you now. I have kept some data here for the ready usage. So let's suppose these are the transactions and these were the items which were purchased together. Now, what do you do in round 1 of a priori algorithm? What will happen? It will pick up all the unique items. These are the list. This is the list of all the unique items here in my list: milk, bread, eggs, butter, coffee, cookies, eggs, and all that. Okay. Now, find in how many transactions butter was purchased. Like you have seen in the total, the last row was total. So this is what I have done here. Butter was purchased 2 times, cookies 2 times, coffee individually, coffee 3 times, juice 3 times, and so on. Now we have to take a threshold, that is minimum support. So let's say my minimum support for these transactions in terms of percentage is 20%. So 20% of the time. Now minimum support count also I should find, that is 20% of 20% of the unique number of items. That is 8. So 20% of 8 will give you roughly 1.6. So let me take it 2. So I'm considering it as 2 after rounding it off. So it means at least 2 transactions should be there to support the occurrence of this item, to validate that these 2 items will be frequently purchased. Minimum 2, minimum support should be 2. See, this is what we have assumed. You have to presume it. Minimum support, you have to, it's just a threshold or benchmark which you have to assume. So here, if you have assumed it to be 20%, that you in your business, it will go as per the business requirements. You can change it and see. So if I have taken a 20% coming to 2, so the transactions which have 1 here, the count as 1. So minimum support count I'm taking not in terms of percentage, this is count. So if the minimum count is 1, these rows will be ignored. So now in round 2, what will happen? We will take these items and we'll form combination of these items. Now butter with cookies. Next, take butter with coffee. 1 on 1. Now keep on taking butter with juice. Next, take butter with bread. This is what we were doing manually, visually when I asked you this question. So same thing, algorithm also will do, but in a predefined step. Now check how many times butter and cookies was it coming? Butter cookies together, cookies and butter. Only one time it was coming. Write it. Butter and coffee together. Butter, coffee, no. Write 0. Butter and juice together. Let me presume. Okay, let's say 2. Butter and bread 0. Now, what is my minimum support count? 2. So this activity will keep on going. Butter will come along with eggs now. Butter will then come with milk finally. Okay, and let's say butter with eggs is 2, butter with milk is butter and milk. Okay, let's take 3. Now again this process will start. I'll start now with cookies. So cookies with the remaining. So now I'll take cookies and combine it with remaining. Then I'll take juice, combine it with remaining, and so on. So this list will keep on growing here. Okay, and you find the count of it. Remove the transactions. In the next step, these will be removed because their minimum support count is below the threshold, below the minimum support count. These rows will not be considered. So this manually works. 2 and 3 will be kept. So let's say now this will remain, these 2 will remain. In round 3, what will happen? You will combine these now, butter and juice with eggs this time. Butter and juice, butter and eggs. So butter is common, so I'll take butter, juice and eggs now. Next, in round 3, I'll be taking butter, juice and eggs this time. And repeat the same process until we are exhausted with all the combinations. Okay, and the final result which you get becomes your frequently occurring item set. Let's go back to this course. See, this is for our understanding. We do not have to do it manually, but you should know what is happening so that when we are using it in the algorithm, otherwise we'll have Python libraries will provide us with the direct usage of a method will be there which we'll import and start using it. This is a plot which tells us the same thing as we have seen in the last table, that most frequently purchased item is foot mat. Depicting it graphically also you can see. So it shows us, this is the bar plot, which shows us that foot mats were purchased most often. Now, how do you claim that people who have purchased foot mats will also purchase seat cover? If they have purchased seat cover, they will purchase foot mats. If they have purchased foot mats, they'll purchase mud flaps. So we have to find all the possible combinations and minimum support and confidence for these transactions. So let's say support, we already talked about what is support. So mathematically, what is support? For a transaction. Support is number of transactions which contains both x and y divided by total number of transactions. So let's say if see minimum that was about threshold which we have assumed, like how I took now minimum support or minimum support count, that was a threshold. But now here we are finding support for each of the transaction in case of x and y. Let's say we are saying that x determines y. That is, if a person is purchasing foot mat, see here, if a person is purchasing foot mat, there is a probability that the person will purchase car cover or seat cover as well. This is what we are trying to identify. So for this, we need to calculate, we need to have appropriate support and confidence. So how do we find support? Find the minimum, find the number of transactions that contains both of these values. where foot mat and seat covers come together. Let's say there are 3 such transactions. Upon total number of transactions, assume that is 10. So this becomes your support for your transactions. Percentage, if I just multiply it by 100, what will it give you? It will give you percentage, number of times these two items were purchased together. This is one way of looking at in how many transactions out of the total transactions, both the items were purchased together. So maybe you can say 30, if 3 transactions out of 10, both of them were purchased together, you got a 30% support from your data that they will be purchased together, only a 30% support. But whether you want to claim for it or not, now how to check whether 30% is enough or not? This has to be, compared with some threshold value. For that, we have taken minimum support and minimum confidence. So now confidence is another matrix to answer these types of questions. Confidence finds number of transactions which contains both X and Y, that is 3, and divided by total number of transactions which contained only X value. Here, also, see example is taken, given here, we'll see that same example. Now look here, for the example, if between association between foot mat and seat covers, whether they will be purchased together. If foot mat is purchased, seat cover will be purchased or not. See here, X determines Y is not same as Y determines X. If a person has purchased foot mat, will he purchase seat cover or not? If you are using only the support matrix, if you use only support, look at the formula we have used. Number of transactions that contains both. That is, there are 3 transactions which had foot mats and seat covers divided by total number of transactions 15. If I do the reverse, I'm interested in knowing people who have purchased seat cover, will they also buy foot mats? Will my formula will not be the same? Will my support will be the same or not? It will be same 0.2 only because of this calculation, because of this formula for support. This idea how we find this matrix support is number of transactions which have both the items divided by total number of transactions. So X determines Y and Y determines X will be same. Support will be same for both of them. So, but it doesn't means logically, if you think people who have purchased foot mat might purchase seat cover. Like if I purchased a phone, I might purchase a cover, but not the reverse. If I have purchased a phone cover, is it likely that I'll purchase phone also? No. So logically, it doesn't sound well. It doesn't fit in, isn't it? So we need another matrix apart from support. So this will give you that confidence where uh, there are 3 transactions where both are occurring. Numerator is same in both the case, but this time look at the denominator. It is X. Number of times X comes in your data. So this will differentiate either you are talking about X determines Y or Y determines X, because it will be different. Confidence will be different. I hope this part is okay. Our confidence will be different for both the cases. In this case, if I'm trying foot mat to seat cover, this is 6. Maybe seat cover was purchased in 4 transactions. That might be 3 by 4. That might be different from this value. So confidence here we are getting is 0.5. A confidence of 0.5 indicates that means 50% of the customers who have purchased foot mats will also purchase seat cover. Have also purchased seat cover. But whereas support was telling us that 20% of the customers purchased both of these things together, foot mats and seat covers. Confidence checks first of all, how many people have purchased X, the main item. Out of that, how many people have purchased seat cover? So that probability is different. In terms of set, if you want to write notation wise, you can see support is written as X union Y, because it can be X union Y can be written as Y union X also. Confidence is Y by X. Confidence tells you how many times people will purchase Y given X. So now to find to get to some analysis, we need to compare it with some minimum threshold. So you have to choose it. See, you can choose it to be point when that is 10% of the transactions or 20% of the transactions based on your data, based on your business requirement, based on your analysis. See, this is what analysis is. Analysis cannot be fixed up. You take 10% and then go ahead, deploy your model. No, you have to keep on checking whether it's working good for 10% threshold or it's giving you it's working well for 11 or 12% or 15%. So it's a job of data analyst to keep on varying these things and come to an appropriate model which fits the business requirements in the best possible way. Okay, see, you can read this. Another example here. So support for, let's say we are looking for association between, if a person has purchased audio system along with toolbox, two things together the person have put in the basket, will he put a Windows tint or not? Okay, so here this becomes your X. People who have purchased audio system toolbox purchasing window tint. So number of transactions where all three are coming together is 2. Number of total transactions is 15. That is 2 by 15 becomes your support. Number of transactions containing all is 2. And where only audio system toolbox comes together is 2. So see, confidence here is 1. What does it mean? With the confidence is 1, that means with 100% confidence you can say that people who are purchasing X will also purchase Y. And that's another question. People might not have, more number of people might not have purchased it. See, support was less. So it's just telling us that it might be possible that many people have not preferred for purchasing these two things together, X together. But whenever they have purchased, confidence tells us whenever they have purchased X, they have purchased Y also. This is what confidence tells us. Now here the same example has been summarized in the form of this table, in the form of a two-way table, where we have already seen support was coming as 0.133 and confidence was coming as 1. If we make a two-way table for it, so here it is telling there are two people who have bought audio system in toolbox. So there were two people who bought window tint, and out of these people, 0 didn't buy. So there was total 2 people, and both of them have purchased. 2 people purchased audio system toolbox, and out of them, in both of the transactions, window tint was also purchased. That is why 2 here. Now, did not buy audio system and toolbox together, but they purchased window tint. Do we have such occurrence? Till now, we have not seen, we have not taken into account the case where people purchased only Y. We talked about people purchasing X and Y together divided by people who are purchasing X in confidence. But it might be the case that there are transactions where people purchased only Y, only window tint was purchased, only a mobile cover was purchased. Maybe there are more number of such transactions where people purchased only the phone cover, but they didn't purchase the phone. So what is that data telling us? So in order to bring all these things to look at the data from different perspectives, we have different metrics like lift, conviction, leverage are also there. And these are the formulas. They all come from different combinations of the initial matrix which we have studied, support and confidence. So if you divide confidence of X and Y by the support of Y, we get this lift. You can see here for seat cover and foot mats, the lift component is coming to be 1.875. All right, so this is just a combination of confidence and support. To include that matrix, consider people who have purchased Y. Maybe there are such transactions that might also add some meaning to your analysis. So confidence with which you can say that people who have purchased seat cover will also purchase foot mats is 0.75, and only the support for foot mats. What is support for foot mats? How many times people have purchased foot mats, isn't it? So out of 15 transactions, only 6 times it happened that people purchased foot mats. Support of Y. When you divide it, we are getting 1.8. So here's a comparison chart. If this lift matrix is 1, that means X and Y are statistically independent. So X might not have any influence on the presence of Y. If lift is greater than 1, which in our case it is coming to be greater than 1, that means X and Y are positively associated. If it is less than 1, then they are negatively associated. Here is that same example for a priori. So we have items, item 1, item 2, item 3, and the same thing they have tried to explain here. So if this is implemented, let's go to the fourth and see. Okay, this is just a summary. Okay. Lift is another matrix. See, what is support? What is confidence? They are ways in which we can analyze the data, analyze the associations between the data. We are doing the same thing. See, this topic is association analysis. We are still finding associations between items. Whether you have purchased one item, will you purchase B also or not? So, support is also telling you in some way how many times the two items were purchased together. The other matrix, confidence tells us how many times the person purchased X. The people who purchased X also purchased Y. Lift is taking Y also into account, and lift will talk about consider the people who have purchased Y also individually, and maybe you can consider dividing it by the people who have purchased Y to get to some matrix to for this analysis. We have two more which have not been included here. So these are different ways of analyzing. Support and confidence is what you will find mostly used in this, because the most famous a priori algorithm also we use support and confidence to get to this calculation here. See, support, if you know support and confidence, lift, leverage, and conviction can be calculated from these two. So it's important to understand these two. See, it's just everything we don't need to do by hand now because data sets can be big. So what we are doing here is we will just use this technique a priori. We'll import a priori from this ML extend package and use it here and just supply our data set to it. So this is all preparing your data set. Here we have groceries .csv file which you can import, split it, clean this and data set, encode if required, and then you can directly give it to the a priori algorithm to find the frequent item sets. It does all the job. We don't have to do anything manually. So now when you can check the confidence matrix also. This tells you the support, confidence, lift, leverage, and conviction. This can generate a summary. The model which you have created here, the frequent item sets which you have find, you can check the rules also, the matrix, by using the summary method as well. So here you can see the complete summary for all the items which were there. So here you can see when support for each item, confidence, lift, leverage, and conviction is also coming. This is the complete summary. I hope you're able to read it. It's saying if the person has purchased whole milk, whether the person has purchased other vegetables or not. So there's some text called other vegetables. Similarly, the person who has purchased other vegetables have purchased whole milk or not. So they might not be same. You can check. See, support will be same in both the case because we talked about this. Why support is same. Confidence might not be the same here. Because it's not the reverse is not reverse might not be true. So this is the complete summary for all the transactions. There is a quiz. I think we are done with this market basket analysis. If you have not understood a priori algorithm, you can go. I think in detail that algorithm is not explained in this course. You can go to YouTube, check any video on a priori algorithm. You will understand. It's not that difficult. We'll go to the today's topic, that is regression analysis. You can search this in Springboard. Link will also be shared with you. I hope the screen is visible. This is the prelude section from where you can download all the datasets and demos. These are the courses which you should be aware about. These are the terms which are used in this course. So I think these you have already done. Plotting also, you know. Hypothesis testing. See, one we have seen how chi-square test works. We have some other type of tests like z-score test, t-test, f-test. If you which will be used in this course, I'll try to explain you that what are these t-tests and f-tests doing. It will be almost similar to the test which you have seen in case of testing for normal distribution, Shapiro-Wilk test. You remember we have just imported that package Shapiro and used to check whether the data is normally distributed or not. Quite similar analysis is quite similar to that, but these are some different tests which we'll be talking about here. So if you're okay with it, that's fine. Otherwise, you can go for the courses like statistical inference using Python or statistics, some statistics course you can go through to understand these terms in detail. This is, see, regression analysis, the course name itself tells you that we will be focusing only on the different ways of regression analysis. You have already studied about simple linear regression and multiple linear regression. We talked about what it is, and I hope you remember all that discussion where we talked about this equation of line y is equal to mx plus c in case of simple linear regression. Do you remember? Simple linear regression, where we had only one predictor and one target variable. So a simple linear regression model can be represented as y is equal to mx plus c. This equation is same, y is equal to mx plus c. Don't get scared. This is mx, this is your c, and some error component which is attached to it. So in case you have only one predictor variable, that is, if your k is 1, that means you are going for simple linear regression model. Otherwise, if it is more than 1, that means you will go for this type of equation, same equation. Now it just becomes m1 x1 plus m2 x2 plus m3 x3 and so on. As many predictors you have, this will keep on adding. Your c is intercept and your error component, which we have added some random error. Is added to some noise or random error is added to this model. This is coming from the previous course itself, and we talked about relationships as well. So linear regression models work on some assumptions. We will talk about those assumptions here. First of all is when you can use those algorithms, the first thing itself says they're linear regression models. So the relationship between the variables should be linear. You plot a graph, this is a scatter plot, and see whether the relationship is linear or not. So the first graph shows you positive linear relationship, second one shows you negative linear relationship, but still linear. Third one is not linear. You can see there's no line. You cannot write an equation of line to depict these points. The pattern which is coming here is in the form of a curve, which is clearly not a line. So now what will happen if I have this data and I fit a linear regression model here, I will still get some value of intercept and coefficient. It will try to fit your linear regression model which you have used will try to fit this data and come up with an equation of line which will not give you correct answers because data was not linearly related. And we didn't do this analysis earlier, okay? Linear regression models should not have significant outliers. So outliers, like if you plot data, you find some points are going here and there. So that becomes difficult to come up with an equation of line if we have such outliers. So generally what happens, we get rid of these outliers. Outliers understanding, you can draw a box plot also if you remember to get rid of these outliers. Check of how many outliers we have because they can totally change the meaning. I hope you remember from that discussion if we have only one single outlier that changes the whole data. Like if I simply talk about me, I have some values. I have 2, 2, 3, let's say 3, 4, and I have one big number, let's say 50, which is my outlier. And now find mean of this. If I find mean of this, somewhere it will come around 3. But now what if I find mean of all this? Mean of all this will be so high. Mean of all this numbers will be so high, which is not close to 3, isn't it? So this might be this might be misleading that mean of all the observations is, let's say, close to greater than 30. What if this mean comes greater than 30? Whereas the mean was only 30. I can exclude this one person and then find the mean which will give you an accurate picture of the data, which is 3, accurate mean that is 3. This is what this understanding is required so that we can remove the outliers from the data set priorly and then remove those outliers and see if a linear regression model can fit easily and we can get to the statistics. Next assumption for these linear regression model to work is that the observations should be independent of each other. That means the observations in the rows. See, you had these data points now. Like I have X and I have Y. Y is your price. So you have some matrix here, 4 bedrooms, and this is lake view, okay, and this is price. Now 5 bedrooms, lake view, and the price value here. Okay, so data rows, these rows should not be dependent on each other. This row should not be dependent on any other row from your data. This row should not be depending on any other row from your data. So they should not be interrelated. They should be independent. These rows, these observations should be independent of each other, and one should not be determining the other. Then we can go for these regression models. Next one is the residuals or residuals here. This word will come so often, so you just understand what it is. Residue means difference between the actual value, that is y, and the predicted value, that is y hat. So I hope you know we fitted model, then we calculated the predictions. There was training data set. This is the data set. We divided into 4 using train test split, if you remember. And these are our y values, actual y values. And then we predicted y hat values also. So difference between the actual y values and the predicted value for each and every row. So if I have 200 rows in this data set, I'll have 200 such values, 200 error values, isn't it? I'll have 200 error values. We are calling these error values as residues. Okay, as residues. These residues should not exhibit any pattern. They should be, they should have equal variance. They should be equally distributed on the data set. Like how you can see in this plot, there are 3 plots here. Here you can see, let's say the best fit line is the middle one. Okay, this line is the best fit line. When you plot the errors, now these are not the data points, these are the errors which are plotted here. There are separate plots which will help you plot these residues. In fact, we have a residue plot. You have regression plots, you have residue plots to plot these error components. So this is a residue plot where we have plotted errors with respect to maybe the y hat value, the fitted value. So this is, maybe you can assume the error that is residue. This is a error residue plot on your y-axis versus your x-axis is the y fitted. The fitted values of y, predicted values of y versus the errors. So now when we have plotted these errors, it shows a pattern in a shape. Like it's earlier it was close to the best fit line, but now we can see it started spreading outwards. So there's a fixed pattern which it is following. As you go right side towards the x-axis, it started expanding. So there's a pattern to it, or it started decreasing. Errors are showing a pattern, whereas in the last one you can see the errors are equally distributed around the best fit line, starting from the what is this y hat values? Those 200 values. So let's say we have predicted our predicted y hat value was 15 lakhs, then it was 16 lakhs, 17 lakhs. So predicted value is this, and you calculate the difference between the predicted and the actual value and plot it here, is what we are doing. So it should be equally distributed for all the data points or all the rows. If it is equally, if the errors are equally distributed and they do not exhibit any specific pattern, we say that the data is homoscedastic. That means it exhibits equal variance across all distance, all the instances, all the rows of your data. So we have used this scatter plot to see. And if it is not homoscedastic, then we say that if it exhibits some conical pattern, or if it totally expands or starts, contracting towards the line, then we can say that the data is heteroscedastic. So regression algorithms will work well for homoscedastic data, not for heteroscedastic data. That is what we can check before implementing a regression algorithm. Okay, this is assumption 5. Now this this heteroscedasticity might be because, let's say, you are studying over a period of time, over a period of 50 years, how many people have, like how many times online transactions have started. So if you take this data, let's say I'll take few data points. Let's talk about 1950. Year 1950, online was not there. Year 1960, maybe 1 or 2 people were using computers. Let's say, let's not talk about online transaction was not there. 1970, maybe 20 people started using. 1980, okay, and so on. But now if I start taking the data from 2000 onwards, or you say 1990 onwards, maybe it will be a huge difference. See, it was 0 here. This now, let me take 10,000 people started using, and add one more 0 to it now. Come 2010, you can add one more 0 to it now, isn't it? 1, 2, 3, 4, 5. Come 2020, you can add one more 0 to it now. Now, let's say I want to compare this data, year versus the number of people who are using computers. I want to find, is there any relation? So let's say I want to predict what in 2060. How many people will be using computers in 2060? If from this data I'm trying to get this answer, look at the variation. Let's say this is the data and you have used linear regression model to fit this. Now, linear regression line would be somewhere close to the maximum values. If I plot this, if I plot this value year versus your number of customers, number of users, let's say, number of users, it was less, then it was high, then as the time has increased, it becomes too high, isn't it? It becomes too high, and if you start finding the error component for this, then it will show the pattern as we see in heteroscedasticity, because errors will be too high. Maybe the line fitted will be closer to these values because they are higher order values. And if you start finding errors, now compare, predicted value would be close to this. Well, let's say your if you take a mean, also mean of these values, that will be, if I take mean model, okay, forget about what regression will do. Let's take mean model of this. Mean will come somewhere around, let's say this, or maybe this also. If I assume mean and now find error component, difference between 10,000 and 0 is too high. Difference between this and this might not be too high, but difference between this value which I have taken as mean will be too high in comparison to 0, 2 and 20. So there you will see such kind of a pattern. In these cases, we should consider treating our data set prior to the regression analysis. Maybe you can consider, rather than considering number of internet, number of computer users compared to the year, maybe you can go for number of people who had year wise, let's say people who in a particular area per capita, you can calculate, let's say location wise, how many people were using computer. Restrict or refine your, the variables, the x variable or y variable. We have to work on it. We have to get this. The error should be um, like this. When plotted, the residue plots, when you do it on a scattered plot, then it should show equal variance. It should not exhibit some pattern like this. Next assumption is, which we have already discussed in the previous sessions, that is normal distribution of data. The residuals, that means the errors of the regression line when you fit it, after that some residues come, no? After your regression, when you fit the model, those residues should be approximately normally distributed, should exhibit normal distribution. So normal distribution, there are ways to check normal distributed data. Normally distributed data is one which is centered around mean values. So if you consider your mean error would be 0 here in this case. So let's say this is the point 0. This is your point 0. So normal distribution of error means it should give you a bell curve. So all the errors which you plot for this data should lie somewhere around the mean value of this, that is 0. Mean value for errors will be 0. Mean error should be 0. So either your error should lie till here, maybe, probably, or this is based on deviations, how far it deviates from this, but it should be closer to the mean values. It should be normally distributed towards both the ends. What if it is unequally distributed? This type of other type of distributions might be, maybe it is skewed towards this side or towards the right side. That time we can say the data is not normally distributed. Now, plotting it and analyzing is so difficult, we cannot trust our eyes. So what we can do is we can go for the statistics, which plotting also you can do. So if you want to go for plots, we can go for QQ plots, like which it has been mentioned here, normal QQ plots. So they are called quantile plots to check whether data is normally distributed or not. So that can be done. Box plots also you can use to check normal distribution of data, or you can go for histograms, or you can go for some statistics, like we have used Shapiro-Wilk test, or There are other ways also. You have different types of tests given by different people. Anderson test, Koglomerov test. We have used Shapiro. Maybe we'll be talking about that only here. This is what we have already studied, the same example here, units and minutes. This, I hope you remember, we already talked about this. Three models we have taken based on the assumptions of M and C values and then compared those values to see how. Now, how do we find the predicted values of M's and C? What has to be the value? If we cannot assume M's and C's, there has to be, these algorithms have to compute some best fit value of M and C, that is your V1 and V0. They have to get that best fit value. How will they get that best fit value? Let's see. The internally what is used. First, we have to find errors. The basic goal is to minimize the errors. See, you have the original values. You have original y values and you have predicted values. Let's say for one instance, I'm considering y minus y hat. This gives you error. I hope you remember this is error is actual y value minus the y hat, or the reverse you take it. Now, these errors cannot be taken as it is, because we have seen when we find errors and when we take a summation of these errors, they get to nullify each other. I hope you remember. So positive errors and negative errors will nullify each other. And if you are taking this matrix sum of errors, sum of errors, if you take for comparison, there is a problem that the errors will nullify each other and will always give you somewhere around zero, a sum number which is around zero. So we square it, correct, Kushbu? So we have to square it so that we can get rid of that negative positive problem. Square it and then find sum of it. So when we do that, that becomes SSE, sum of squared errors. Square these errors. This is only one. Find sum of it, no? Find sum of it. That is 1 to n. For all the numbers, for all the rows, find this. Error square sum. This is called sum of squared errors. Okay. So here, this formula is yi minus y hat square and sum of I from 1 to n. Now here what we have done, replace this predicted value y hat with mx plus c. That is bx here. If you replace this, it becomes minus bx minus c. Is it okay? This is actual value of y and this is predicted value of y. Just we are replacing this by mx plus c. That's it. Okay. So the predictions actually. So to find now, how do we say, how do we get to the appropriate values, the best fit values of a and b in this equation? In this equation, if we minimize this component for different values of a and b, if I can find a minimum SSE, a point, the values of A and B, which gives me minimum SSE, would be my answer in this case. That means the ultimate job now is to minimize the sum of squared errors. Now we have an equation in differential calculus. We have a way to find local minimas and maximas. First order differential, if we find first order differential of any equation gives you a point of local maxima or local minima. Have you studied differential calculus? I know it's difficult to remember it, but some idea? See, I also don't remember all the formulas, all the rules, but we will not go into those rules of differential calculus and all. But I hope now you are a simple example of differential. Let's take an equation. Let's say I have my y is equal to x. Okay, let's say it is 6 plus x square. Let me take okay, we'll not do this way. We'll take fx. Let's say this is a function fx and you have 6x minus x square. Now, when you have to take a differential of this, that becomes d of fx with respect to x. I want to take a differential. What will it be? This becomes 6 minus 2x. Differential, very good, Astha. Right, you remember. This becomes 6 minus 2x, correct. So now, this is first order differential. When you equate this first order differential to 0, now equate this to 0, you get x is equal to 3. This is your critical point. This is your critical point, which tells you either this point is a point of local minima or local maxima. That is another question. How do you find local minima or maxima, whether it is minima or maxima? But it gives you that local point of minima maxima. If you want to check whether it is minima maxima, what you can do, take a value which is lesser than x is equal to 3. Take x as minus 1. Oh, sorry. We'll take positive values. Take x as 1. So when your x is equal to 1, put x is equal to 1 here in this equation and tell me what is coming. 2, 6 minus, correct. If x is 1, my fx becomes 4. Now I'll take one bigger value. If x is 5, now what is 6 minus 2x? 6 minus 2 times of 5. Minus 4, correct. Now it is coming minus 4. And I know x is equal to 3 is my critical point. I am going my data at this point, x is equal to 3. Your data is going from positive to negative, isn't it? From positive to negative. You take any value of x which is less than this critical point, x is equal to 3, you will get a positive value. You take any value of x which is more than this critical point x, I'm getting minus 4 here in this case for this equation. So I can say at critical point, I am going from positive to negative. That means when I will plot it, maybe I was going positive, positive, and I started going at negative. So this is the point 3. At point 3, my curve changes to negative. At point 3, my curve changes to negative. Now this curve tells us this is the point of local maxima. This is the point of local maxima, where maybe you can say errors will be maximum in our case, but our job is to find the point of local minima. So this equation is giving us a point of local maxima, but our equation, when we equate it to zeros, it gives us a point of local minima, because there your curve would be like this. So when you find a critical point, our job is to find those values of A and B from this equation, at which we'll get a local minima, that means least error. We want to find a point of least error from this equation. So maybe our errors were earlier negative, and the differential equation was giving you some negative. First order differential was negative, but then it started becoming positive. So when it moves from negative to positive, graph would be this. Plot a graph to see. It was negative, negative, it suddenly started going positive. So that means curve should be like this. And now it will give me a point of local minima. Okay, so coming back to this, we have to differentiate this equation with respect to first of all A and then B. These are the 2 points of interest. We want to find A and B, point at which A and B would give you the minima, not Y and X now. Y and X are of no concern. We are concerned about A and B now. So first you differentiate it with respect to A, then we differentiate it with respect to B. Okay, do not get into all the statistics. What is interested to know is, that is intercept. Finally, intercept, that is C, is this. Y bar stands for Y mean of Y values. X bar stands for mean of X values. Okay, and how you can calculate coefficient is this equation finally, and this is coming from top. This is coming when we differentiate those two equations. Now you should know the rules. You have to go back, read all that differential calculus, how we differentiate these two equations with respect to some variable. Keeping all those formulas and all everything in mind, we get to the b value as this, and from b we can derive the intercept also, that is c. So here you can see these, what are these values? Xi, yi, some values of xi, yi. You will have individual values of xi, yi. Find a summation of all these values xi, yi. This is x bar, y bar, n is number of observations, xi square. In previous, I don't know whether they have used it in this course or not. Let me check. In previous course where we talked about regression, this is there. This is there. You can check here. Same formulas which we have used. They have first calculated numerator and then denominator from that formula. Then divide it to get slope, that is m. Use it to get the c. This becomes your c and m. This is this we don't have to do. This is just for our understanding how things are working. Because if we go and fit our model, it will directly give us the value of coefficient and intercept as we have seen. I think the topic has changed here. Yeah. Okay. Hmm. We have calculated it using formulas manually here, but when you fit the model using some linear regression model, you can get the values of intercept and coefficient. That code is not here. You can take it from the previous regression course. Now use these values of m's and c's here to get to the equation. This best fit model can be used to get the predicted values on all. Corresponding to units, we have plotted minutes, the actual time, and the predicted time for these based on the best fit model. We have linear algebra course, we have statistics, calculus, exactly calculus, I don't know. I have to search. I'll send that list to Prithvi. Maybe she'll share it with you. The appropriate course in Springboard, I have to search. But by name also you can search linear algebra or linear algebra using Python. If you search, it will come. Statistical inference using Python, I think this course also should be there. If you want specific link, I'll send it to Prithvi. Okay, coming to the next bit of it. See, this is about understanding the relation between two variables, how you can understand using different statistics. Like we have used chi-square, if you remember, chi-square test to determine relation between two variables. We calculated we found chi-square statistic, that chi-square gives you chi-square statistic. It gives you p-value also, probability, where we have used that significance level to determine whether the two variables, whether the two things are related to each other or not. I hope some part of it you can connect if you remember. So there was 0.05 which we have taken as significant value. There was a chi-square statistic coming and there was some p-value coming, probability value coming. And initially there was an assumption. So we have assumed that our x and y were independent. Remember, in chi-square test, x and y were independent, and exploiting this, that x and y are independent. So this is called as your null hypothesis. Assume that x and y are independent. I'm talking about chi-square, not about this, so that you can relate it with chi-square. X and y are independent, and then we have found the probabilities of x and y appearing together, provided that they are independent, using the probability. And we have plotted it, compared it with the actually occurring values to get to these statistics, the chi-square statistics and the p-values. Now, if the p-value, which is coming from our data, was coming less than our chosen significance level, that is 0.05, if it is less than this, then we have to reject the null hypothesis. If it was coming greater than 0.05, then we can say that we can accept the null hypothesis. That means they are independent. So we assume something, that we have initially assumed that they were independent, and then we were gathering enough confidence for this statement that they are independent. So if we get more than 5% of support, then we can say that they are independent. If we did not get even 5% of the support that they are independent, we will reject our null hypothesis that they were independent and conclude that they were dependent. X can determine Y. This is what we were doing in chi-square statistic. Hypothesis testing is same whether you use chi-square statistic or F test, P test. These are T tests. They are different ways of analyzing. In different situations these tests are used. So here also we will be using T test to determine the relation between two variables. So this hypothesis testing, H0 stands for null hypothesis. Now assume that we have this equation, okay? If you say that y is not dependent on x, y does not depend on x, then can we say that beta 1 will be 0? Isn't it? If I have to assume that y is not dependent on x, see, our job is to prove y is dependent on x. We are interested in knowing whether it is dependent or not. So one hypothesis we have to form, that let's take that they are independent. They are not dependent. If they are not dependent, we know directly we can go to this equation and equate b1 to 0. So that means our null hypothesis says that b1 is 0. So here we can use t-test to check this. And t-test, you don't have to do anything like how we have imported chi-square model and used it directly. T statistic can be used in Python to calculate the t statistic value and the p value. It will come. Okay. It's just that we have to now understand what that numbers tell us. If this, when you calculate both the values, the value of the test statistic, either it is chi-square statistic or t statistic or f statistic or z-score test statistic, it can be anything. It will also give you p-value. So if it is from using both, we can determine, using both we can find whether the null hypothesis is true or it has to be rejected. But P is actually a little easy for us to use because we know P is related to our chosen significance level, which we have chosen. Test statistic should be compared with the value which comes from chi-square table. You remember there was a table in chi-square where I told you you can check this whole table on internet. You type chi-square table, it comes. Similarly, we have T statistic table, we have F statistic table. So if you want to understand, if you want to compare using the test statistic parameter, then you have to find that critical value from the table, from the predetermined table. So this is actually a little tricky to compare. So we ignore this and go to the p-value to check whether our assumptions made in the null hypothesis are correct or not. Now, if the p-value exceeds the chosen level of significance, that is, if it is, usually it is 5%, so that's why 0.05. If it is more than 5%, then we can say there are more than 5% chances that whatever you have assumed in your null hypothesis is true. Okay, so then we cannot reject the null hypothesis, we have to accept it. Otherwise, if there's not even 5% of the support, not 5% of the data supports your argument that they are independent, then we have to reject it and say they are dependent on each other. Critical and p-values. See, critical values, if you want to know, in this course it has not been talked about, but you go to the chi-square test, comparison between categorical variables. There's a table. Have you gone through that component? Comparison between categorical values? Okay, I'll take you back to the guys, if you have doubt, please put it in the chat window and please mute yourself. Request everybody to please mute and put your questions in the chat window if you have them. I'll show you how do we get to the critical value. Let me go to the old course. I hope the screen is still visible to you. Prithvi, are you there? Can you please mute people who are speaking? Can we mute the audience?
గౌతమ్ నీకే దాసుకుని మాట్లాడితే ఇప్పుడు
I hope the screen is visible. I have come to the chi-square page. In the previous topic, that is association analysis, you'll find this page. And this is how you find this statistic. Now let's focus only on this. First line is a chi-square statistic value. This is what we called as chi-square statistic. So similarly, when you are using t-test instead of chi-square test, you will get some value like this, which we are calling as test statistic. In general, this value is called as test statistic, which is specific to the test you are doing. Here we are doing chi-square test, so this is called chi-square test statistic. If you will go for t-test, that will be called as t-test statistic. If you're using f-test, this will be called as f-test statistic. So in general, we are calling it as test statistic. This, as well as the next one, which is the p-value, can be used for final inferencing and comparison with your hypothesis testing. How? Now let's say this p is coming to be this one, 0.0012. If I have chosen a significance level of 0.05, now my chosen significance level is this. Compare it with this and tell me whether it is less or more. It is less. The p-value which is coming from here is lesser than the chosen significance level. What does it tell you? It tells us that there is not even 5% of the support with which I can say that what I have assumed in my hypothesis is correct. Not even 5% support to support this null hypothesis. So less support. So what will I do? I will reject my null hypothesis. What did I assume in my null hypothesis in chi-square test? That both the variables both the attributes were independent. This is what we assumed. So a lesser value of P statistic tells us that reject null hypothesis. You see, graphically, if I have to tell you, maybe this will help you. Let's say this is my, if I have to plot it, let's say this is my chosen significance level, that is P. So if your P, and here also it is two-way actually. If my P value comes less than this, that means my P value will lie somewhere here. Okay, it will lie somewhere here. That means it is very less than my chosen significance level. If it lies here, if your P value lies here or your P value lies here, that means you can reject null hypothesis. You have to have this much of support which lies within this range from here to here in order to approve your null hypothesis. And again, it calls for the standard deviation. These points are actually representing your standard deviation, where it says, you know, the golden rule, 68%, 65% of your values should lie within one standard deviation, 95% lie within two standard deviation, and maybe 99.5% of the times it should lie within 3 standard deviation away. So maybe you can consider this point as 3 standard deviation away, and at least that much support you should have, at least 95% support you should have, is what we are considering. You can go for this also, you can go for this also. So we are gathering support. Now this is one way of checking. The other way around is this 35, what you have got here. Now this 35, this 35 here tells you this point. Now this is a point of significance level 0.05, which numerically represents 35. Which numerically represents 35. Now there's a, not 35. This point represented by 0.05. What does this point represent on this x-axis? This is called as a critical point. Critical point, how do you get? Critical point you have to get from this table. Where has it gone? Page 3. Where is this table? Page 3. Page 2. This is the table. Okay. So this is this table you have to refer to get to that. What is the point on the x-axis which is represented by 0.05 significance level? Which is that point? So we have to consider this, our significance level. Look at this table and go for 0.05 significance level. This is the significance level. Now it is dependent on the number of labels which you have in your x and y's. So number of rows, if you go back and check page number 1, number of rows was number of labels in x. Number of columns is represented by number of labels in y. That gives you 3 minus 1 into 6 minus 1, that is 10. So here we are considering degrees of freedom as well to get to this critical value. If you have chosen significance level as this and degrees of freedom is 10, that means your critical point becomes 18.31 in your case. It is 18.31. Now remember that graph which I plotted just now will not come. I have to do it again. Let's do it here. See, this is my graph. Let's say this is the point which I'm calling it as of 0.05 significance, and this is the point on x-axis represented by 18.31 in your case. And now my test statistic is giving me what? 35. If you remember, chi-square test statistic was coming to be 35. This is till 18.31. If your test statistic comes less than 18.31, then only we can accept the null hypothesis. If it comes more than this, if it goes outside this range, so 18.31 is this, 35 will be somewhere here. It is lying somewhere here. So if it is more than, if this test statistic is more than the critical value, reject null hypothesis. Reverse, you have to check. P has to be less than the significance level to reject null hypothesis. Test statistic has to be more than this critical value to reject the null hypothesis, that they are independent. I know this is a little confusing, so maybe you can go to some statistical inference or statistics to check how to interpret these hypothesis testing. We'll go back to the regression course from where we stopped. Where is that? Okay, now coming back to this, our null hypothesis was what? We assumed that slope is 0. That means y and x are not dependent on each other, correct? Now let's see. We have used one model here, that is OLS model. This is ordinary least square method. It is widely used in regression techniques to check these statistics. So you can use this OLS model dot fit to create a model, just like we were importing linear regression. Instead of that, if you want to check these statistics, we can go for OLS, which works on the principles of least squares. So from that equation, it is coming. Model dot summary of this data gives us, this is the F statistic. So if you have more than one variable, you can go for F statistic also. The table is different for T statistic and F statistic. Some calculations and numerical formulas are different. So, but approach is same. Probability, it gives you two things. Test statistic and p-value, which can be used for comparison. We'll focus on p-value because we know significance level will be 5%, that is 0.05. We'll focus on that. We'll not go by F statistic here because otherwise we'll need those values of F test, critical values also. Now, this is, don't get confused, it is not 8.92. You have to look at e raised to the power minus 13 as well. So in all, this becomes 2 less than 0.05 when you check. If it is very less than 0.05, what will you conclude? This p-value from F statistic is lesser than 0.05. It means what? It means if this is 0.05, it lies here. It lies here. If it lies outside the range, what do we have to do? Reject. Reject the null hypothesis that they are independent and conclude that they are dependent. This is reverse actually. You have to go back to what you have assumed. You have to see what you have assumed in null hypothesis while rejecting this. Reject null hypothesis. Hypothesis was that they were independent. So reject that they are independent and assume that they are dependent. They are depending on each other. Looking at T values. So this P for T, you can check here. This is coming to be 0 for in case of units. Units giving you minutes. So we have checked it for units. The T statistic for units is coming to be 0, which also shows us, which is very less than 0.05. This also tells us that it can be rejected. Null hypothesis can be rejected. This is the T statistic value. So if you know critical value, this can also be checked. Okay, this we have already seen. Score, you remember? Finding model dot score, which gives you coefficient of determination. Again, that same discussion has come here. You can go through it again. What is SSE, sum of squared errors? I hope most of you have already studied it in the last course. Sum of squared errors, that is same. y predictions minus y hat. We have two other components, SSC and SST. So they are just the variations. So sometimes there are three things you'll use here. You'll use actual values of y, you will use y hat values and y mean values here, y bar values. So these SST, SSC, SSC are different combinations of maybe one is finding y minus y predicted, one is finding y minus y mean, the other one is finding y predicted minus y mean. So maybe this is SSE, this is SSE, this is SST, this is SSR, sum of square derivation. And to find score, to find the accuracy of the model, to find this coefficient of determination, which tells you whether variability in your dependent variable can be explained because of the independent variable. This is R square, which is called as score, model dot score, which we were doing. Formula for this is this. Either you go for this or you go for this. So coefficient of determination ranges from 0 to 1. If it is near to 1, that means the model is useful. And it can be, variability can be explained. Doing it manually, and so here they have done it manually to show you that it is coming to be 98% of the variability which is observed in time taken to repair the computer, that is minutes, can be explained because of the predictor variable. Analyzing the residuals for checking for homoscedasticity, and also you can plot RSQ should be root mean square. Where was it, RSQ? Oh, this is R square. RSQ here is R square. Just a variable name. Again, we have one more way. See, we have talked about enough matrix, and it's not that the matrix which are available are good enough, or we cannot come up with any matrix of our own. Different people have different ways of analyzing and comparing, and this is one another way to standardize this formula of finding the residues. So this is called as standard residual formula for y hat for the predicted values. So this is what if you can see, what is numerator? Isn't it y hat? The original y hat. Residue for y hat. Actual formula. We have just divided it by the sum of squared errors divided by n minus k minus 1 to keep this component also into the picture. What if the number of predictors increase or decrease? What if the number of rows increase or decrease? So the number of rows and columns also should have a role to play in all these calculations of your errors. So in order to incorporate that, we have standardized these residues by including this. Here, this is calculating. Here, what they have done, this part is implementing this formula. That's it. You can check it and relate to it. This is taking square root, finding, dividing, all that. That formula is implemented here in Python. That's it. Now, of this, we have used regression plot here to plot our predictions, the predicted values versus the residues, standard residues, which we have calculated in the previous page. Rather than just doing y minus y hat, we have taken the standardized residual values versus the y hat, the actual predicted y hat values we are comparing to plot this residues. So these are residues which are plotted here, and you can see they are. Is there any pattern which you can see of these blue dots? Are they forming any shape? Are they diverging? Are they converging? Or any conical shape here? No. They look uniformly distributed towards the best fit line. So we can say that this data is homoscedastic. This plot is called scale location plot, the plot between the residues and the standardized residues and the fitted values. We are using the scale location plot here. Another plot, different way to do this. So there we were using regression plot. This time we are using direct residue plot to do this. So residue plot, you don't have to find anything now. See, earlier using regression plot, we were computing the residues and then we were doing it here. When you use residue plot, you don't have to do it. Just give units and minutes, data set from where it is coming, and it will do all that writing, finding residues and all that, and it will plot this residue plot which we expected. So here also, using this plot also, we can confirm that the data is homocelastic because it is not showing any pattern. See, if your data is homocelastic, it tells us that data has a linear relationship. This is also one of the inference when we find for homoscedasticity in the data. They are connected. They should be linear, and if they are homoscedastic, they tend to be linear. Now, how do we prove that? We have deliberately taken an equation which is not a linear equation, data in such a fashion which is not linearly connected. So, randomly, some data points from 1 to 100 we have taken and taken square of it. Y is equal to x square is the equation. This is not linear equation. This is quadratic equation. So now let's try to fit this data x and y values on a linear regression model. Import this linear regression, create instance of it, fit your data. Don't go quadratic, but still let's try to fit it. Now make your predictions on the actual values. We are not doing that train test split and all, just to keep it simplified. Predicting the values of y corresponding to the x values, check for the intercept and coefficient, it's coming to be this. Now look, it looks so 101 times of x minus 1717 something. That's what I was saying. Some data it will give you. It's not that it will not work. It will work. It's all about calculations, and you have some numbers. Something will be calculated. Some value of m's and c's will come. Let us plot it to see what it gives. So this is the residue plot here from the Seaborn library. Residue plot on these x and y values. When you plot, you can see this is the best fit line, and it follows a specific pattern. All these residues, they exhibit a specific pattern, and this pattern is not a linear pattern. So residues were first decreasing, then they suddenly started increasing as the input increases. Okay, fine. Normality can be checked using Shapiro test, as we have done in the previous course, or here you can use some plots also. Here we have used a QQ plot to check for the normal distribution. So we can use this prob plot. It's not named as QQ plot, though it is called as QQ plot, but in Python library, you will find this in stats packages. Stats.prob plot we are using to plot the residual errors of see, this is original values, computer minutes. That means the original y values minus the predicted values, that is the y hat values. So this becomes residue errors, and we are plotting here these errors using a prob plot, checking for normal distribution. So here, if these values, if these dots, the blue dots, they are all almost aligned towards this line, the red line, isn't it? They are almost closer to this point, which shows that the data is quite normally distributed. This is one way to check using QQ plots. Okay, we have included here Shapiro test, which we already did. So on this residual error, if you invoke this Shapiro, you get two things. One is test statistic, and the other one is the p-value you get. So stat and p, two things you get. Test statistics, first is this, and p. We'll not go by statistic, we'll go by p, which is coming to be 0.8. So here, what can you say? P-value is lesser than your significance level or higher? It's higher. 0.8 is higher than your chosen significance level. So what does it mean? Can we reject the hypothesis or accept the hypothesis? If p-value is greater, that means if p-value is chosen greater than the chosen significance level, it means accept the null hypothesis. You have got enough support, more than 5%. You have got 8% of the support for your assumption in the null hypothesis. Go back and check what have you assumed. We have assumed that data is normally distributed. Data is normally distributed. So that means we have to accept. It means we cannot reject. See, though it is too less, support what we have got here is too less, but still we cannot reject null hypothesis. And you will find this term. That's why I'm telling. They will not directly say accept null hypothesis. This is not the term used. The term used is we cannot reject null hypothesis. See, null hypothesis, now you can come and say, let me take the reverse, let me take null hypothesis is, my sample is not normally distributed. Let me take this, let me invoke it on Shapiro and get to my conclusions. We cannot do that. How do you decide it? Go back to your chi-square test and now imagine, why have we taken the null hypothesis that they are independent? There is a reason for it. I cannot take the reverse. Can you go there and say my null hypothesis is that data are dependent? Apply find statistic and then say they are dependent or not dependent. I cannot do that because there's a formula based on which that chi-square statistic is calculated. That formula, that probability calculation calls for independence between the data. You remember? I explained you that time. How if the two data are independent, if the two variables are independent, then only you can apply that formula. So internally, I don't know what is the
possibility of repetition in bias and something that is bias is used and probability.
I'm sorry if you're asking a question. Your voice is not clear.
Possibility.
No, can you jot it down in the chat window? Or if some other person who can hear it properly can write in the chat window and send the question.
Anything will do it.
Nita, I hope you have got your answer. Null hypothesis, basis for null hypothesis, what you are to take in null hypothesis has to depend on the understanding of what does the test do. What is the internal processing of the test? We will not go into what Shapiro does. I have also not gone into this. What we have to do is just understand that, take that data is normally distributed and okay, moving on. We have, I'm sorry if you were asking a question, I couldn't make out anything what you were speaking. Please write in the chat window if there was a question.
Hi, Sonam.
Yes, we have.
Yeah, your screen sharing.
Yeah, I stopped it to mute some people. Now, has it come?
Yes, yes.
Mhm. All right, so simple linear regression, multiple linear regression, we have talked about, and we have discussed also in the previous course, where we just have to keep a check on these things, some conditions or assumptions we check, and then we go for creating a model using multiple linear regression or simple linear regression or OLS you can do. But now, what if the data we can we implement linear regression if the data is not linearly dependent, like how we have an equation here, fx is equal to c times of exponential, it's of the order of exponential, e raised to the power minus dt. Doesn't look like the data is linear. It doesn't look as if the data has a linear relationship. So, but there are places, there at times we can convert these kind of relationships to linear relationships, and then we can apply regression on it. Like how, if you remember, we have done it on logistic regression. Logistic regression is a class of classification algorithm. Prithvi, can you please mute these people? Can you mute everybody from the background? A request to all of you to please keep a check on your mic, guys, when you're talking. Guys, again, question. Do you remember logistic regression? What we were doing in logistic regression? Logistic regression expects you to predict some class 0 and 1, let's say. Whether the person will have hard disease or not, whether the email will be spam or not. In terms of numbers, binary data or maybe categorical data you are collecting, but still we can use, we have a algorithm called as logistic regression, which is underlying which uses regression technique. But there, how do we use it? Or in the situations like this where we have exponential equations, so we can transform these equations to some linear equations and then use linear regression algorithms for this. Like how we have taken a log value, take log on both sides. Taking log on both sides gives you this. Now, can we consider this as log of WD as y and log of C as your intercept and your minus D as your coefficient, that is beta 1, and then your this T value as it is. Looks like, isn't it? It looks like that the equation, this equation can be transformed to a linear equation when we take a log of it. So we will model this equation, we take logs of it, and we will then create a linear regression model for these components. For this equation, we'll create a linear regression model, and then to finally predict the actual values, we will do the inverse. Earlier, what we have done in the first step, we have taken log of it. Now, if you want to go back to the original stage of exponential, we will take exponent of it to the original values. So, our original predictions will become this. There, internally, what we have used here, e raised to the power mx plus c, where your beta 0 plus beta 1 plus t, where these are your b0 and b1s. So these equations of exponential orders can be transformed using the law. Here we have an example. You can go through this. We have usability of tires. So how many miles the tire has been used for? 10 miles. Percentage usable is 64. If the tire has been given 20 miles, percentage usability is 36.5. This is the data. Right? Now here you can see the data is not linearly related. You can find that from the visualization as well as the test which we have done so far. Here we are plotting it to see whether the data is linearly related. The plot. So this plot can be represented as the relation between the percentage usability and the miles driven can be written as like this. We can take a log of both sides to transform this equation to normal y mx plus c equation. So take a log of both sides and we get log beta 0 plus b1 times of miles driven. now we use our same regression algorithms to fit this model. We use those same algorithms. So we just have to decide our x and y now. My x, that is my predict variable. This is my predict variable, which remains same. There's no transformation required for this. We use it as it is. My y variable, that is this is my y variable. This y requires a log. This is the log time. So we take a log of the values of the y and then give it to the model for learning. Okay. We are using here OLS so that we can get these test statistics as well here. So here in OLS, how I get this formula, the values which you see on the left side of this symbol. This is the symbol here. The left side value is y and the right side value is x. Previously it was just for visualization. Now here is what we are doing. We have custom model and actually we are doing here. Pick up the data of reliability and add this model OLS or model is so our model will be created on x and y values. X remains same. Y we have transformed because we have taken a log of the y values. When we did Hershakti, we might have observed on the data set if you go back to the data. Here, let's be the same file variable. Take the log value of this log of y. Take the log of y. So what we have discussed from the mathematical calculation is taking the values which will come here A, B, C, D, D. There is a linear relationship between these two values. Though there is no linear relationship between these two values, but still there is a linear connection between y and y. This is what we have studied, and this is the what we will require to do the inference, do the predictions. I'm going back to this screen. Then generate summary of this model. So again, it gives you a statistic and the D statistic value, normality ratio. So if you understand the test, job KPI test, these are the tests for all of the results we have created. I also know about this. Now you have got the values of M, and C of coefficients. And you can check the usability of the model. Say R square gets 0.9888. So you remember what is R coefficient of determination. Adjusted R square, which accounts for the inflation, which comes due to the number of increases in the number of attacks. So adjusted R square is also quite good. 0.996. That means 98% of the times this variability can be explained. This is your intercept is 4.666 and efficient for minus analysis. Put it here this formula. Now to find the log of the percentage using values. So the value predicted value which you should get will be log of the percentage using. Now if you make predictions, we have get the transform back values. To take exponential of it to make the calculations. So which is beta 0, E times of beta 1. So originally equation was 0, E times of beta 1. This was originally y. So here this comes the final equation. Say that plot you are seeing here looks like negative relationship. It looks like negative relationship because look at the points which are generated. We have miles versus log of percentage usable. Log of it. They are linearly related. There is a negative linear relationship. That is why we are able to exploit. If you avoid doing miles driven and only percentage usable, you will not give this. It becomes something different. There's a few log like this is this is a predicted line. Scatter plot of miles versus maybe log of percentage given with their predicted values, which shows that is quite linear. Say now you have to prediction for 25, your prediction would be this point. My line is not just you. This is your point, which will be quite linear to be actually get points. Okay, extending the discussion of relationship polynomial relations. We have polynomials. So in polynomials, you can see their relation like the x can be we can take a quadratic equation or the equation which is of higher order. So how do we do? How do you plot? Or let's say quadratic equation. What if I find a linear relationship and quadratic relationship between the linear values and they are plotted? We take an example here. Here we are doing some example. There's a relationship where you want to predict the volume of the cubic feet based on the girth. This is the relationship which is identified. Okay, let's check. So this is the polynomial relationship where we cannot want linear relationship. So now let's plot a linear relationship. Sorry, let's start again. So the relationship between limited volume or quadratic equation. Use LS to plot this and cubic volume, the cubic feet volume, the y value which we want to predict, and this is your this is your x value based on which you want to predict. These are your predictors. In your predictors, you can see here it is girth in inches plus meter times of girth square. So like if you want to express some numbers, they are actual mathematical expressions if we have right. It cannot be written directly in formula. Formula treats all these symbols differently. They have different meanings for all these things. So when we have to use this formula to make it understand that this mathematical calculation, this I is being used here. This function I tells it that it has been calculated. So we have use OLS OLS technique that is ordinary least squared to fit this polynomial table, it can be used because it is observed that OLS comes with one function of the least